Welcome to the deep dive. Today we're really digging into something fascinating. What happened in Indian science after the incredible work of Aryabhata?
Yeah, it's a period that often gets less attention, but it's crucial. We're looking at how ideas evolved, how they were challenged, built upon. It wasn't static at all.
Exactly. We've got some amazing sources that show this wasn't just about accepting genius ideas. It was about debate, critique, refinement. A real intellectual conversation stretching over, 1,000 years?
At least. And we're going to focus on two key moments, or maybe periods. First, there's Brahmagupta in the 7th century. He really took a critical look at Aryabhata.
Okay, so the critique comes fairly early on.
Relatively speaking, yes. And then we'll jump much further ahead to the Kerala school, mainly flourishing between the 14th and 16th centuries. Just incredible mathematical leaps happening there.
So this deep dive is all about tracking that thread. How did science progress within India? Not just one big discovery, but this ongoing process, full of, well, probably some arguments and surprising developments.
Absolutely. It's this dynamic that's so interesting. You see later scholars directly referencing, sometimes arguing with, sometimes extending the work of those who came before. It's a living tradition.
Okay, let's dive in then. Brahmagupta. He's roughly a century after Aryabhata.
That's about right. We usually date his major work, the Brahmasphuṭasiddhānta, to around 628 CE. And it's a huge, comprehensive text on astronomy and mathematics.
But he didn't just present his own system in isolation, did he?
No, not at all. That's what's really key here. He specifically included a chapter called The Examination of Systems. And in it, he scrutinizes other astronomical models.
Including Aryabhata's.
Oh, very much so. Aryabhata's system was a major focus of his critique. It shows he wasn't working in a vacuum. He was actively engaging with the leading ideas of his time, even if he disagreed with some of them.
That itself says something about the scientific culture, doesn't it? That critique was part of the process.
Definitely. It highlights that even revolutionary ideas like Aryabhata's aren't just instantly accepted everywhere. There's a process of, well, scrutiny. People compare them to what they already know. They raise objections.
So where did Brahmagupta really diverge from Aryabhata? What were the main points of contention?
Probably the most famous one, and certainly one that stands out, is his rejection of Aryabhata's idea that the Earth rotates on its axis.
Right, the spinning Earth theory. That was pretty radical back then.
Hugely radical. Brahmagupta, however, stuck with the more traditional view, the consensus view really, of a static, unmoving Earth at the center of the cosmos.
Why though? What were his arguments against a rotating Earth? It seems counterintuitive now, but it must have seemed compelling then.
His arguments were very much based on, let's say, common sense physics, or what seemed like common sense at the time. They actually echo arguments made elsewhere, like those attributed to Ptolemy much earlier.
Such as?
Well, he argued, for instance, if the Earth is spinning really fast eastward, shouldn't an object thrown straight up land way off to the west? Because the ground moved under it while it was in the air.
Okay, I can see the logic there, based on everyday experience.
Right. And similarly, wouldn't birds flying west struggle to get back to their nests? Wouldn't the nests have moved significantly eastward underneath them? And he also mentioned things like arrows shot vertically. He felt the rotation would cause them to deviate significantly. Basically, the observed world didn't seem to show these expected effects of a rapidly spinning Earth.
So his conclusion was, we don't see these things happen, therefore the Earth must be still.
Pretty much. It seemed to contradict direct observation and, established physical understanding. Instead, he favored models that explained the movement of the stars and planets differently.
Like what? If the Earth isn't moving, what makes the sun and stars appear to circle us?
He supported models like the Pravaha wind concept. This idea proposed that there are these immense, powerful winds circulating in the heavens.
Winds in space.
Sort of cosmic currents, yeah. And these winds were thought to carry the celestial bodies, the stars, the sun, the planets around the stationary Earth. It's a different mechanism to explain the daily motion we observe.
Fascinating. A completely different physical picture. Okay, so the Earth's rotation was a huge point of disagreement. Were there other, maybe more technical differences in the numbers, the calculations?
Oh, yes. There were definitely numerical disagreements, too. Brahmagupta used slightly different values for some key astronomical parameters.
Like what sort of parameters?
Things like the exact number of revolutions the moon makes within a larger cosmic cycle, a Mahayuga. These might sound like tiny details.
But they add up in the calculations, right?
Exactly. Over long periods, even small differences in these fundamental constants can lead to noticeable discrepancies in predicting planetary positions or eclipses.
Accuracy was the name of the game.
And what about those big cosmic cycles themselves, the yugas? Did they agree on the structure of time? That's another really interesting divergence. Brahmagupta stuck to the more traditional Puranic view, where the yugas within a Mahayuga have unequal lengths. Krita, Treta, Dvapara, Kali yugas getting progressively shorter.
Okay, the traditional breakdown.
Yes, but Aryabhata had proposed something quite different, that all 4 yugas within the cycle were of equal duration.
Why would Aryabhata do that?
Well, later commentators who followed Aryabhata, like Bhaskara first, seemed to appreciate the mathematical simplicity and symmetry of the equal yuga system. It made calculations potentially cleaner.
So maybe a clash between sticking to tradition versus seeking mathematical elegance.
It could well be. Brahmagupta might have felt it crucial to align with the established cosmological narrative, while Aryabhata and his school prioritized perhaps a more streamlined mathematical framework. It shows different priorities at play.
Interesting. And I think I recall reading something about pi as well. A difference there too.
Ah, yes. Pi, always a point of interest. Aryabhata, as we know, gave that remarkably accurate value of 3.1416.
Which was way ahead of its time.
Absolutely. Brahmagupta, however, in his work, sometimes used the value square root of 10, which is roughly 3.1622.
That's less accurate. Why would he do that if a better value was known?
Well, the context seems to be important. He seems to have suggested Sendhan particularly for more practical geometrical problems, maybe related to construction, land measurement, things like that. It's computationally simpler than 3.1416.
Ah, so maybe it was a trade-off. Precision versus practicality for specific tasks.
That seems like a very plausible explanation. For high-precision astronomical calculations, the more accurate value is essential. But for rougher, everyday geometry, perhaps Sendhan was considered good enough and easier to work with. Aryabhata's focus was clearly on astronomical accuracy.
Okay, so Brahmagupta mounted quite a comprehensive critique. Cosmology, parameters, even practical maths. It sounds quite adversarial. But you said earlier it was productive. How so?
Immensely productive, despite the critical tone. Firstly, it's clear Brahmagupta didn't just dismiss Aryabhata, he studied his work very closely.
How do we know that?
Because he actually adopted and even elaborated on some of Aryabhata's most important mathematical contributions. The big one is the Kuṭṭākāra method.
Kuṭṭākāra, what's that?
It's a really sophisticated algorithm for solving certain types of equations, linear indeterminate equations, sometimes called Diophantine equations. Basically, equations where you're looking for whole number solutions. Aryabhata laid out the method, and Brahmagupta clearly understood its power and used it, even refined aspects of it.
So even while arguing about the shape of the cosmos, he recognized and used Aryabhata's mathematical tools. That's quite nuanced.
It is. It shows a selective engagement. He could appreciate the mathematical brilliance even while rejecting the cosmological conclusions. That's healthy science, really.
And what about the impact of the disagreement themselves?
That's perhaps the biggest long-term effect. These disagreements, especially over fundamental things like Earth's rotation or the yuga lengths or key parameters, they didn't just disappear. They sparked debate.
Kept the conversation going.
Exactly. For centuries. Later astronomers had to grapple with these different viewpoints. They couldn't just ignore Brahmagupta's challenges or Aryabhata's innovations. They had to choose sides or justify their own positions, maybe find better arguments or evidence.
Did this lead to distinct schools of thought?
Yes, absolutely. This is where we see the formation of different astronomical traditions or camps, known as pakas. You have the Ārya-pakṣa followers leaning towards Aryabhata's system.
In the Brahmagupta.
Following Brahmagupta's system. And it wasn't always as strict either situation. Some later astronomers were quite eclectic.
How so?
Well, they might use, say, Aryabhata's more accurate value for the length of the year, but prefer Brahmagupta's model of the cosmos. Or they might try to reconcile the differences, maybe average parameters, or create hybrid models that try to incorporate the best features of both.
So the critique forced people to think harder, to justify, maybe even to synthesize.
Precisely. It prevented Aryabhata's ideas from becoming dogma, from being accepted passively. Instead, it ensured a dynamic, ongoing scientific conversation within India. Brahmagupta, in challenging Aryabhata, inadvertently ensured his ideas remained central to the discussion for centuries.
That's a fascinating perspective. The critic actually solidifies the importance of the original work by engaging with it so seriously.
It often works that way in intellectual history, doesn't it? Strong critiques often lead to stronger defenses or more refined alternatives. It fuels progress.
Okay, so that sets the stage brilliantly. We have this period of debate, critique, Different schools forming, all stemming from Aryabhata, but pushed forward by figures like Brahmagupta. Now, let's leap forward. Several centuries later, South India, the Kerala school. This sounds like a major shift again.
It really is. We're talking roughly 14th to 16th centuries, centered in what is now Kerala. And it's an absolutely remarkable period for mathematics and astronomy.
And how does it connect back to Aryabhata and Brahmagupta? Is it a continuation of those debates?
It's very much framed, especially by the Kerala scholars themselves, as a continuation and refinement of the Aryabhatian tradition. They saw themselves as inheritors and developers of Aryabhata's legacy.
So after centuries of the Aryapaka and Brahma-pakṣa existing, perhaps side by side, the Kerala school represents a powerful resurgence and advancement within the Aryabhatian lineage.
That's a good way to put it. And they took it to astonishing new heights, particularly mathematically. They developed concepts that, quite frankly, anticipated discoveries made in Europe much, much later.
Like what? What are we talking about here?
We're talking about the development and use of infinite series expansions for trigonometric functions: sine, cosine, arctangent.
Infinite series. We've got to break that down a bit.
Right.
How does that differ from what Aryabhata was doing with trigonometry?
Right. Aryabhata had developed these incredibly useful sine tables. He calculated sine values for different angles using a method based on essentially step-by-step calculations from one value to the next, what we might call finite differences. It gives you a list of values.
A table you can look up?
Exactly. What Mādhava of Sangamagrāma, the sort of foundational figure of the Kerala school in the 14th century, did was different. He found ways to express these functions, sine, cosine, and particularly the arctangent function, not as a table, but as an infinite sum of terms.
An infinite sum. How does that work?
Think of it like a recipe with an infinite number of ingredients, where each ingredient adds a little bit more refinement. For the sine of an angle, Mādhava found a series: add this term, subtract that term, add the next smaller term, and so on forever. The amazing thing is, this infinite sum adds up precisely to the correct value of the sine.
And you can stop adding terms whenever you want.
Well, the more terms you add, the closer you get to the true value. So you can calculate the value to any desired degree of accuracy just by calculating enough terms in the series.
That sounds incredibly powerful compared to a fixed table.
It was a huge conceptual leap. It's moving from discrete values to a continuous functional representation. And these series he discovered are mathematically identical to what later became known in Europe as Taylor series expansions for sine, cosine, and arctangent.
Developed centuries later by people like Taylor and Gregory.
Yes, precisely.
Okay.
Mādhava and the Kerala school got there first.
Wow. Did they use these infinite series for anything specific? Any famous results?
Oh, absolutely. The most famous is probably Mādhava's use of an infinite series for the arctangent function to calculate the value of pi.
He used his series to get pi. How accurate did he get?
He calculated pi to at least 11 decimal places. Some analyses suggest maybe even 13.
11 decimal places in the 14th century.
Yes, think about that. That level of precision for pi wasn't matched anywhere else in the world for nearly 200 years. It's just staggering.
It really is. It shows not just the power of the mathematics, the infinite series, but also incredible computational skill to actually calculate that many terms accurately.
Absolutely. It's a landmark achievement in numerical methods. It wasn't just a theoretical curiosity. They could use these series for incredibly precise calculations.
So Mādhava is the key figure who kicks this off. Did others in the Kerala school build on his work?
Yes, definitely. His work laid the foundation for several generations of brilliant mathematician astronomers in Kerala. Two other really important names are Nīlakaṇṭha Somayājī and Jyeṣṭhadeva.
Okay, what were their main contributions?
Nīlakaṇṭha Somayājī, who lived into the early 16th century, wrote a very important commentary on Aryabhata's Aryabhatiya called the Tantra Sagraha, and also his own commentary on it. This again shows that deep connection back to Aryabhata, but Nīlakaṇṭha was incorporating the new mathematical tools and refining the astronomical models.
Refining the astronomy. Did they stick with Aryabhata's spinning Earth or Brahmagupta's static Earth? Or something else?
This is where it gets really interesting. Nīlakaṇṭha proposed a revised planetary model. It was essentially geo-heliocentric.
Geo-heliocentric.
Meaning the Earth is still the stationary center, but the 5 visible planets, Mercury, Venus, Mars, Jupiter, Saturn, they orbit the Sun. And then the Sun, carrying the planets with it, orbits the Earth.
Wait, that sounds familiar. Isn't that similar to the model proposed by Tycho Brahe in Europe later?
It is remarkably similar, and Nīlakaṇṭha developed his model in the late 15th or early 16th century. significantly before Tycho Brahe. It seems to be an independent development.
That's incredible. Why propose that kind of model? What advantage did it have?
It offered a better explanation for the observed motions of the planets, especially things like the apparent retrograde motion, where planets like Mars seem to stop, move backward for a bit, and then move forward again. Nīlakaṇṭha's model could account for these complexities more accurately than the purely Earth-centered models, while still keeping the Earth stationary, which perhaps felt more intuitive or philosophically acceptable.
So it's a sophisticated attempt to reconcile observations with a plausible physical system without making the full leap to a sun-centered universe.
Exactly. It's a major step in theoretical astronomy.
And the other figure you mentioned, Jyeṣṭhadeva.
Jyeṣṭhadeva is fascinating. His work, the Yuktibhāṣā from around the mid-16th century, is truly unique.
How so?
Because it provides the proofs. It lays out the detailed logical arguments and mathematical derivations for many of the theorems and infinite series discovered by Mādhava and others in the school. Most earlier Indian mathematical texts tended to state rules or theorems without extensive proofs. Yuktibhāṣā gives the why.
So it's like a textbook explaining the reasoning behind the results.
In a way, yes. It gives the rationale, the Yukti. And another remarkable thing, it was written not in Sanskrit, the usual language of scholarship, but in the local language, Malayalam.
Malayalam, why would they do that?
It strongly suggests an intention to make this advanced knowledge accessible to a wider audience within Kerala, perhaps students or practitioners who weren't necessarily masters of Sanskrit. It points towards a concern for pedagogy and dissemination of knowledge.
That's amazing. Developing calculus-like concepts and writing detailed proofs in the vernacular. It paints a picture of a very intellectually vibrant and perhaps even outward-looking community.
It really does. Now, we have to be careful, of course, when we talk about infinite series and these methods. It's not quite the same as the fully formalized calculus with limits, derivatives, and integrals that Newton and Leibniz developed later in Europe.
Right. The framework is different.
The formal framework, the notation, the explicit concept of a limit, those weren't quite there in the same way. But the core idea of using infinite processes to achieve approximations and exact values, the development of these specific infinite series, that was undeniably a huge achievement and a sophisticated precursor to calculus.
So they were exploring the territory, mapping out key landmarks, even if they didn't have the exact same coordinate system we use today.
That's a great analogy. They were deeply exploring the power of infinite processes for computation and understanding trigonometric relationships and applying it to astronomy. It was incredibly advanced mathematics for its time, built firmly on the foundations laid by Aryabhata centuries earlier.
This whole journey then, from Aryabhata's initial breakthroughs through Brahmagupta's critical engagement in the branching schools, all the way to the Kerala school's stunning mathematical insights. It's quite a story.
It really is. It shows Indian science wasn't monolithic or static after Aryabhata. It was this dynamic, evolving tradition.
The key takeaway for me, and hopefully for you listening, is just how vibrant that intellectual life was, characterized by, well, rigorous debate, building on the past, and continuous innovation over more than a millennium.
Absolutely. It wasn't just preserving knowledge, it was actively wrestling with it, challenging it, and pushing its boundaries. From Brahmagupta forcing a deeper examination of Aryabhata's ideas,
To Mādhava and Nīlakaṇṭha using Aryabhata as a launch pad for entirely new mathematical and astronomical territories. It really highlights Aryabhata's lasting impact, not just for his own discoveries, but as a catalyst, right?
a catalyst for centuries of further thought, debate, and discovery within India. His work set a benchmark and sparked conversations that led to places he himself probably never imagined.
Which leaves us, I think, with a really interesting thought to ponder.
Yeah.
As you listen to this, think about how this specific dynamic, this interplay of critique, continuity, and innovation within the Indian tradition, how does that compare to how scientific ideas developed in other parts of the world you know about?
Yeah, what does this long conversation, stretching from Aryabhata through Brahmagupta to the Kerala school, tell us about the nature of scientific progress itself? How essential is that internal dialogue, that willingness to challenge even foundational ideas for moving our understanding forward? Something definitely worth thinking about.
A perfect place to leave it. Thank you for joining me on this really enlightening deep dive.